Hello viewers, myself Dr. T.N. Oza here. I am going to present to you a new video based on some basic points about chemical kinetics. This first video will be followed by a number of other videos on the same topic so as to clarify this very important topic, both theoretical aspect as well as the numerical aspects. So let us proceed. Introduction first. Chemistry is primarily a subject that studies chemical transformations which a variety of reaction conditions or variables like the concentration of various chemical species present in the solution or the partial pressures of gaseous species, temperature, pH of the medium, dielectric constant, viscosity, intensity of radiation for photochemical or radiation-induced reactions, ultrasonic frequencies, time period, and of course, the type of species involved, including their physical state, particle size, surface area, polarity, etc. We will discuss in systematic manner. In chemical kinetics, we mainly focus on the rates of chemical changes, its feasibility, reversibility, non-feasibility, etc. That is energetics is discussed under thermodynamics. Thus, both these branches, thermodynamics and chemical kinetics, are complementary to each other. As regards the rates of various chemical species, various reactions, some are immeasurably slow, some are slow, some are fast, and some are very fast or instantaneously. Accordingly, a variety of analytical methods based on some suitable indicator parameter to be measured have been employed or monitored. Some methods employ traditional chemical analysis, potentiometry, polarimetry, colorimetry, etc., while some others are so fast that sophisticated methods like in situ spectrometry, NMR, EPR, temperature jump method, flash photolysis, etc. are used. For a better understanding of the step-by-step reaction mechanisms, collateral data from the thermodynamic studies are necessary. Let us now proceed to mathematical formulation of a rate equation. We will begin with very simple ideas. In general, the rate of a chemical reaction does not remain uniform throughout. In one of the graphs later, this has been shown. Obviously, simple statistical method would not suffice. We need to apply differential and integral calculus for this purpose. For a hypothetical chemical reaction in which reactant A giving product B, initial concentrations in mole per liter at time t equal to 0, concentration of A can be indicated by small a or C0, and for P it is 0 when T is 0. After time lapse of T, the reactant concentration decreases to A minus X, Ct, T refers to time, and product concentration X becomes greater than 0. Rate law formulation is R equal to minus dCA upon dt. Here dCA represents infinitesimally small change in concentration of reactant A, and dt represents correspondingly small time period. The negative sign indicates decrease in concentration. If we want to measure the rate in terms of product concentration, we can write dCp upon dt or dx upon dt. Note that whether we use reactant concentration at a given time t or product in concentration at the same time, the rate should be the same. The only difference is when we choose reactant, the negative sign is put to indicate decrease. When we put product, then no negative sign. It means concentration of product is increasing. For a general case, AA plus BB giving IL plus MM, velocity plus minus R can be written like 1 over L PCL over dt equal to 1 over M PCM over dt equal to 1 over A dCA equal to dt equal to 1 over B dCB equal to dt. And rate R equal to Kn Ca raised to power P Cb raised to power Q. Here Kn is called velocity constant of order n, and the superscripts P and Q refer to the order of particular species in the reaction. While reporting rate of a reaction, the prevailing conditions of temperature, pressure, solvent, etc. must be indicated. Now regarding velocity constant Kn, suppose concentration of both A and B in the above equation is unit liter per mole, then rate equal to Kn. It means Kn can be defined as the rate and all reactant concentration involved in the rate equation are unity. The concept of order of a reaction and molecularity. With reference to the equation 2 given above, P is the order with respect to reactant A, and similarly, Q is the order with respect to the reactant B. Overall order of the reaction becomes P plus Q, sum of all orders. The order of a reaction cannot be read directly by looking at the balanced chemical equation. Instead, it is derived from the analysis of actual experimental data. Therefore, it can be an integer 0, 1, 2, or 3, and a fractional number between the limits greater than 0 and less than 3. Strangely enough, in some cases, the mathematical calculation for order from kinetic data yields a negative value, either integer or fraction. This may look strange, but this is the case because order is obtained from the analysis of kinetic data. It could be both plus and negative. Negative order are very, very rare. On the other hand, molecularity is the sum of the coefficient of reactants molecules in the balanced chemical equation. Order and molecularity may be same, may not be same. For example, in the decomposition of nitrogen pentoxide, dinitrogen pentoxide gas, the balanced chemical equation is written over here. 2N2O5 gas equal to 4NO2 gas plus O2 gas. The molecularity of this reaction is 2, but order is found to be 1. So let me emphasize, order is determined from analyzing the kinetic data. Molecularity is a theoretical term. The only importance of molecularity is during synthesis in this ratio, reactants are to be mixed. And order reveals a lot about the reaction mechanism. Experimental methods in chemical kinetics. Depending upon the nature of the reaction under investigation, an appropriate method is chosen. from over a dozen available techniques. For instance, a reaction involving one or more gaseous reactants or gaseous products, measurement of pressure changes with respect to time is done. Where chiral molecules are involved, polarimetry may be the easiest technique to follow. Inversion of cane sugar is an example of polarimetric kinetics. The other methods are based on measurement of electrical conductivity, spectrometry, volumetry, titrations, chromatography, gas chromatography especially, flow method, flow stopped method, pressure jump method, temperature jump method, NMR method, EPR method, etc. The study of very fast reactions, particularly biological processes, is done using femtochemistry, that is time scale of 10 to the power minus 15 second, based on the measurement of varies of short-lived transient species. So a variety of methods are available. One has to decide which method to use for a particular problem. Method which can be measured easily and dependably. We will now integrate the rate equations. The rate equations written earlier are differential equations. For obtaining practical purpose equations, we need to integrate those equations. When the reactant is represented by A and product by P, the rate expression is minus dCA over dt equal to K1 Ca. As explained earlier, Ca refers to concentration of A, that is reactant. K1 refers to the rate constant. dt refers to infinitesimal change in time, and dCA refers to infinitesimal change in reactant concentration over time dt. So for this simple case, we can write the rate as minus dCA over dt equal to K1 dt. Now we need to integrate this equation. As can be seen, on the left side of equation, there are two variables, concentration and time. On the right hand side, there is one variable, concentration. So first we need to rearrange the equation. We bring Ca on left side and dt on right side. Thus we get equation 1. In equation 1, you see on the left side only one variable, concentration is present. On the right side only one variable, time. Now integration can be done. When we integrate this equation 1, we get equation 2, minus ln Ca equal to K1T plus C. Here this C is an arbitrary integration constant, and natural log Ca is the natural log of concentration of reactant A at time t. Now what we need to do, the constant C is arbitrarily chosen. So first we need to evaluate this constant. For evaluating the integration constant, we apply boundary conditions. Means at time t equal to 0, Ca equal to C0, initial concentration of A. And at time greater than 0, the concentration of reactant Ca becomes Ct, T for time, corresponding time. Thus we derive C equal to minus ln C0. What we have done? We have done put T equal to 0 in equation 1 and Ca equal to C0. Similarly, by putting these values and substitution for C, gives value of C as minus ln C0. Now we can rearrange the equation as shown here very clearly. Ln Ct minus ln C0 equal to minus K1T. In exponential form, This equation can be written as equation 3, Ct equal to C0 multiplied by e raised power minus k1t. Using decadic log system, Ct equal to C0 multiplied by 10 0, 10 power minus k1t. As you know, both exponential form and logarithmic form are reversal of each other. It means rate constant k1 equal to 1 over 2.303 t multiplied by log 10 base a over a minus x. Equation number 5. So this is the most important practical equation. In this, A refers to initial concentration of reactant, that is C0, and A minus X refers to Ct, concentration of reactant at time t equal to greater than 0. For better understanding, we very often plot graphs. So graphical display should be like this. If we plot time along x-axis against log Ct along y-axis, a straight line of slope minus k over 2.303 should appear. And intercept equal to log C0. If natural logarithm system is used instead of decadic logarithm, then the value of slope will be minus k instead of k minus k over 2.3. It makes no difference. Depends whether we use natural logarithm of reactant concentration or decadic logarithm. On the other hand, a plot between the reactant concentration along x-axis and rate of reaction along y-axis, it should also give a straight line passing through the origin. In this case, intercept will be 0 and slope will be positive k. Also, a graph showing changes in reactant concentration as also the product concentration versus time is also included for clarity. You see, product concentration is increasing with time, reactant concentration is decreasing with time. None of these graphs are linear, but the idea how product concentration builds up over time and how reactant concentration decreases over time is shown. These graphs are hand drawn, or better, browse them or look at some standard textbooks. But I would advise you, don't depend on books only. Make a practice of drawing graphs. Only then you can understand which parameter has to be kept where and what is the meaning of the graph. Unless you draw graphs yourself, you cannot grasp the meaning of graphical display. So the legends are shown here. Figure 1a, graph for first order reaction A is to T. First one is between A and T. Rate is dx by dt. The second is between Ca and T. Logarithm of Ca. The third one, rate versus reactant concentration. And fourth one is showing reactant and product concentration both together versus time. Test for first order reaction. From the given data, how can we know whether a reaction is first order or second order or third order? The best method is to use graphical display method or to simply calculate velocity constant using equations for first order or second order or third order. The case in which all k values are the same, reaction belongs to that particular order. Suppose we are analyzing the data using first order equation and getting k1 constant, then that reaction belongs to order 1. If k1 is not constant, then order is not 1. The best method is to plot logarithm of reactant concentration versus time and get this slope. From this slope, we can determine order of the reaction. So as I mentioned earlier also, order is an experimental parameter. It is determined from experimental data. Now we will take up few numerical problems. Numerical problem number 1. For a given hypothetical reaction 2A plus 3B giving 1.5 L plus 2M, we have to determine a number of parameters from this. Concentration of A is given as 0.03 mole per second at a given time. Now we have to calculate changes with respect to B, L, and M also. We have to calculate molecularity and we have to determine order also. Molecularity, as you can see, it is 2 plus 3 equal to 5. It is not the same as the order. Now for determining the respective changes in B, L, and M, first we write the expression in this manner. Rate equal to del A over 2 equal to del B over 3 equal to del L over 1.5 equal to del M over 2. It means if we want to calculate del B, it is 3.3 over 2 multiplied by del A. Similarly, if we want to calculate del L equal to 1.5 over 2 multiplied by del A. Del A and del M will be the same because the denominator is the same. Molecularity I told earlier, 2 plus 3, 5. Now, regarding order of reaction, K1 equal to R1 equal to K, A raised to power P, B raised to power Q. Similarly, R2, it has been given that when concentration of reactant A was doubled, the order was doubled. When reactant concentration A was tripled, the order was tripled. So we can write equation for R1, R2, R3, etc. And by putting R2 over R1, which is 2, you can write the rate equation and you can see R2 over R1 equal to 2 equal to 2 raised power P. Naturally, P must be 1, only then both sides of equation will be equal. So order with respect to reactant A comes out to be 1. Likewise, we can use data for R3 and R2 and calculate order with respect to B is 0. It means overall order of the reaction is 1. It means the rate determining step of the reaction involved only 1, not B. Another numerical problem, analyze the given data for the high temperature gas phase reaction. 2NO gas plus 2H2 gas equal to N2 gas and 2H2O gas. The data are given here. The method of analysis is that first we write rate R1 in equation form, rate R2 in equation form, rate R3 in equation form. Then what we do, we divide the equation for R2 by R1. Then we can get order with respect to NO. Next time, we divide rate for R3 by rate for R2. In that case, we get equation for H, order for H2. Overall order of the reaction will be the sum of both orders. In this case, we determine P equal to 1 and K is also 1 just by using the simple arithmetic. Overall order is 2. Note that the stoichiometry of the reaction does not reflect the order of the reaction. Further, the rate constant K can be evaluated using K equal to rate over reactant concentrations raised to the respective powers. So in this case, K has been calculated like this as shown on the screen. It comes out to be 2.4 liter mole inverse, second inverse. Any of the three set of data should yield nearly the same value for the rate constant. Also, when K is known, rate R can be calculated from given reactant concentrations. Numerical problem 3. Again, a gas phase reaction is given, 2N2O giving N2 plus half O2. And we have to derive the rate constant assuming order is 1. So, number of moles at time t, that is initially, is 1. After a lapse of time t greater than 0, number of moles becomes 1 minus x and x by 2. The total number of moles is 1 plus x by 2. Also, initial pressure of reactant N2O is Pi. After reaction has taken place, total pressure can be given by sum of partial pressures. Dalton's law of partial pressure. So total pressure P at equilibrium is sum of Pn2O, Pn2 and PO2. And as you know, partial pressure in a mixture is proportional to the mole fraction. So we can write P equal to Pi minus x plus half x. This becomes equal to Pi plus x by 2 according to Dalton's law of partial pressure. From this, we can evaluate x equal to 2 bracket within bracket P minus Pi. Therefore, pressure of N2 at equilibrium, Pn2 equal to Pi minus x. Putting the value of x, it becomes 3Pi minus 2P. Now with the rate equation, A1 equal to ln A over T, A minus x. We can put the value of x and we get the final equation in terms of pressures. A1 equal to 1 upon T multiplied by log Pi over 3Pi minus 2P. So for gas phase reactions, pressure measurements are done. Numerical problem 4. Hypothetical reaction, A given P is given. Initial concentration of A is C0, P 0. Concentration after time 40.5 minutes. 25% of A got decomposed. Therefore, Ct equal to A minus x equal to 75%. We have to derive rate expression and calculate the first order rate constant. It is given that the reaction belongs to order 1. Solution. Rate equation minus dCA over dt equal to K1Ca. Power to Ca is 1 because it is said that the reaction is order 1. Now rearranging the equation as above, as earlier we did, and then integrating, we get negative log Ca equal to K1T plus C. Here C is integration constant, arbitrary constant. For evaluating C, we can put T equal to 0, then Ca becomes C0. Thus we can evaluate Ca. Ca equal to minus log ln C0. We can put the value of C and transpose the equation. Thus we can get ln Ct minus ln Co or ln C0 equal to minus K1T. T is given 40.5 minutes. K1 can be calculated as given here, and it comes out to be 7.11 into 10 to the power minus 3 per minute. Problem 5. Find the ratio of time for 99.9% to 50% completion of a reaction of order first. The symbolic reaction is A giving P. Solution using the expression P equal to 1 over K and then C0 over Ct. Here C0 is 100, Ct is 50. In another case, Ct is 100 minus 99.9, that is equal to 0.1. So we put the values for T 50% and for T 99.9%. And divide equation 2 by equation 1. Putting the values, we get the ratio 10. It means if the time period for 50% completion is given, the time period for 99.9% completion will be 10 times more. Numerical data is given, the numerical problem is given, problem number 6. The virus load is reduced by 50% on first washing your hands with soap and water. How many consecutive washings should be required to bring down the virus load to less than 0.1%? The same problem which we solved just now is given, and we can show that if first washing removes the virus by 50%, we require at least 10 washings to remove the virus almost completely. So this is a very useful concept. Now let us proceed how to find the units of rate constant or velocity constant. For the reaction A giving P, rate R equal to dx upon dt. That is K n A power or Kn equal to dx by dt over A power n. Here we know dx is concentration mole per liter, dt is second, A power n is mole power n over liter power n. So we just put these values and find that Kn is mole power 1 minus n, liter power n minus 1, T power minus 1. For zero order reaction, n equal to 0, we get unit mole per liter per second. For first order, unit is per second. For half order, unit is mole power half, liter power half per second. For second order, mole inverse liter second inverse. For power 2.5, mole power minus 3 by 2, liter power 3 by 2 per second. Third order, mole power minus 2, liter square per second. So in this way, we can find the unit of any given reaction if the order is given. The unit of reaction constant or velocity constant can be very characteristic feature of the reaction type. Few other problems have been taken up. Now we proceed to second order reaction. A giving P. Initial concentration of reactant G0 or small a. Product concentration initially 0. After time T, concentration A minus X or Ct, and product concentration is X. Now, rate expression R equal to dx by dt or K2 power A minus X square. I repeat, rate dx by dt equal to K2 multiplied by A minus X power 2. Doing separation of variable, we get the equation dx upon A minus X square equal to K2 dt. Integrating both sides, integration has been done and the rules are also given here, how the integration has been done. So we get 1 over A minus X equal to K2 t plus C. C has to be evaluated using the boundary conditions. We evaluate C, put the value of C in the equation, rearrange the equation, and finally we determine the rate constant equation. So this is the technique. How do we do? Here rate constant K2 equal to X over AT within bracket A minus X. A is initial concentration of reactant, T is time, A minus X is concentration after time T. Suppose we take up the reaction where two different reactants A and B are involved and their initial concentrations are not the same. In that case, a bit complicated equation is determined. How? This has been shown here using partial fraction method. Everything is very nicely explained here. Each and every small step is shown. So by making few practices, you can easily understand them. Let me brief. Dx by dt equal to K2 multiplied by E minus X, B minus X. By rearranging, we get dx upon A minus X, B minus X equal to K2 dt. Now we apply partial fraction method. 1 over A minus X, B minus X can be written as A over A minus X plus B over B minus X. Here A and B are arbitrary constants. We will determine their values later. And when we apply boundary conditions, A becomes equal to 1 over B minus A and B becomes equal to 1 over A minus B. There is a small mistake over here. B is 1 over A minus B. On putting the values of A and B and then integrating, rearranging the equation, evaluating the arbitrary constant C, we get the final equation K2 equal to 1 over T within bracket 1 minus A minus B into log B within bracket A minus X A within bracket B minus X. Here A and B are initial concentrations of reactants. So in this manner, this type of complex equation results. So we have covered some basic aspects of chemical kinetics. I hope these things will be helpful for you. However, practice makes a man perfect. Without practicing these things, you cannot just memorize them. Thank you. Thank you very much.